So now we define the integral of a function, integral as a function, not also as a function. Integral of a function is another function of the upper limit of the former function. And then those are basically indefinite integrals. So what are we going to talk about? First, we're going to talk about integral as a function of the upper limit is indefinite integral and how they're essentially the same thing with varying constants. Then integral of a non-negative function, you get an indefinite integral, and that is always an increasing function because the area keeps increasing no matter what, because it's increasing, keeps getting area. Now, even if it's non-negative function, this area is greater than this area, and this is less than this, and keeps on. This kind of. Then convexity for the convex function, the definition theorems. Then a few theorems for that. Then we prove it, and then finally illustrations. For convex function, I think we do trigonometric sine cos. So let's get into it. Okay, so let's say there's a function f such that its integral from a to b, right, it exists. Okay, so then say 0 or a to x, that's the sine equal to b, afterwards b also exists. So a of x, say it's equal to this function, and it's actually a function of t because if you integrate, it becomes a function f of x minus f of x equal to a of x. Now, why do we say that this is the indefinite integral? Because this f of a can be another not equal to of a1 and not equal to f of a2, where a1, a2 are in that specific range from a to b, but less than x. So then f of x equal to say another function equal to f of t dt. Now the difference between these two functions, that is the difference of these two functions, so then if you think about it by the additive theorem, there's this, which is independent of x. So the difference is always the same. Say, for example, the difference is constant, so that is definite integral. But this normal, where you're integrating from one constant to another x, which you plug in as a variable, is definite. Say, for example, say this, say from 0 to x, t of n dt is equal to f n plus 1, n plus 1, where that function is integral. So you can take any x and this value changes. Now similarly, say here a and b. This is equal to 0 to b t of n dt from equal to a t of n dt, which is oops equal to a b t of n dt is equal to b n plus 1 and say So this is constant, but when you take it from some constant to x, depends on the constant. But basically, it's the same integral if it's integrable function, and we denote that as b to be equal to okay, where f of x is the indefinite integral of we want the limits in. Say, so what does it mean basically? Say you have a function that is a non-negative. This area is always positive. Say from A to B, and say this is a positive area. This positive area is equal to A to B f of t. What if we have a non-negative function like that? So say this is plus 1, plus 2 because it's positive, it's negative 1 from A to B. So the function there from A to B of t dt is equal to sum of area, which is equal to positive 1 plus negative 1 plus positive 2. So it gives you the cumulative. So an integral of a negative function say basically is that area, but of the minus sign. That's the geometry expectation. Also, if we know something of f, say f is a non-negative function again. If you understand a function's property, you can also understand how it affects the indefinite integral. So f is a non-negative function, then you can apply some properties on the indefinite integral. Has some free properties. Say for example, we have a non-negative function and its integral is given by this. This f of t is a non-negative function. Dt, right? And this equal to x2 and f of t dt. Because we have two constants here, if we take it to the other side also, so we get either fx2y is equal to a to y and here. But this, since it's a non-negative function, is always equal to 0. So that means the area of a non-negative function, no matter however, cannot be 0. Say we have a decreasing function, because that will understand if you have an increasing function, it's basically something. Say you have this area which is positive because it's above this, right? And you take a little bit more. This is also greater than this. And no matter how much you take it, say from what point you take it, it's always going to be greater than 0, simply because it's a non-negative function and the area is positive. And as it increases, no matter what, from specific point, is going to increase because you're taking the cumulative. This plus this, even if this is lesser than this, the sum is greater than just the sum. So basically, area increases as x increases. Cumulative, that means the sum of all parts is greater than single previous part. Now we go on to discuss convex functions. So let's discuss the theorem. Before that, what's a convex function? Just intuitive understanding. So say I have an increasing function. So you take some random point here. Say a line. You pick any 2 points on this graph where it's an increasing function, and you draw a line. And that line will always be, that any point on the line will always be greater than or equal to a point on the graph. That's a convex function. And that's convex function. Concave, we have a decreasing function. Same thing, between 2 points. Any point in the line will be lesser than equal to 6. So let's just define it. So definition of concave and convex. So say a function g is said to be convex on that interval AB for all x, y, a member of AB, and for every alpha in the range such as 0 less than alpha less than 1. Actually, less than even less than or equal to 1, because at 0 you have g of x is on that point, so it can be less than or equal to. So I don't know. The book says it's the strict inequality, so we will follow that. Maybe I'm stupid. I don't know. So every point, see, this is the point on the curve g, always less than or equal to some linear combination of g of y plus 1 minus alpha g of x. So basically, what this means is z is equal to alpha y plus 1 minus alpha y. So say we have an increasing function like this, right? Say at alpha equal to 0, say this is x and this is y. At alpha equal to 0, g of y is cancelled out, alpha is 0, so you have g of x at x. And over here, same x, so this is g of x. Then at alpha equals to 1, this is 1 and this is 0, so x is cancelled out, z is equal to y. And similarly, g of z is actually just g of y at 1. So you have this point. Now, since this is actually just a linear combination between these two points of the on a graph, you can just connect it. You don't have to do anything else. So we have that. Now, as you can see, every point on the graph is greater than or equal to this. So if you take 0.5, right, you get the center point, and that is z, which is half of between x and y. So that's basically what concave function means. And we say g is concave with the inequality reverse on AB if this inequality holds. G of z, that means the point on a graph is greater than that linear combination of those 2 points. Any linear combination in those 2 points, that is just linear combination between those 2 points. So basically, a concave function, this point here, x, y, this is always the point on the graph is always greater than this. So that's what concave and convex functions definitely. Now let's go to the proof. First, we need to know that since it's integral using AB, so let x, y be a member of that interval, and as to let them know f is increasing. So we have our condition. Now let z equal to alpha 1 plus 1 minus alpha. Okay, now convex. When to prove it, since increasing, any point on the graph should be less than or equal to the respective one. That is a of y plus 1 minus x. But we know this a of z is actually just like to be added and then you get a of z. So we just take this as alpha a of z plus 1 minus alpha a of z. Because that is equal to that. A plus 1 equal to first one a of y plus 1 minus alpha a of x. Now we shift the appropriate. So we take here alpha and minus. So we take 1 minus alpha a of z here, and we take this three things to become a of x. We take this to the other side, alpha 5 minus a of z. Now we just substitute this. And we integrate the inequality. Now we have an equation function z, z, this is y. Now this is the integration from x to z. That is this. And that is lesser than f of z of dt, which is irrelevant because same thing. But then this f of z minus x is actually this z at this value. And this rectangular structure, clearly this is greater than that. Similarly, take z minus y and the value of z. You get this. And the integration from z to y of function is this. So this is lesser than the whole integration. So that's the next term. So f of z y minus z. Now we also know that z is equal to alpha y plus 1 minus alpha of x. Here you want to find alpha y because we need to find alpha y minus z, some relation. So let that be equal to z minus x minus alpha x. So alpha or y minus z because we care about this interval y minus z in integration. So we just put that as a, and this is equal to 1 minus alpha z minus conveniently. So now we have this. We multiply as inequality. We get this. But this is actually equal to alpha y z. That was the y minus z, which is equal to alpha f of t dt from z to x. So we have proved that this argument, which is the same as so for example, we have the cos function. Okay. Now the integration of this cos function, say from 0 to x, is equal to sine. Okay, so now let's take this cos function. This is from 0 to pi. It's a decreasing function. Okay. And from pi, I think this is 4 pi. It's a increasing function. So in our discussion, if f is decreasing, then the integral of f is concave, which is the case here. Take any point. Similarly, if f is increasing, then any point from here to here is convex. So that point is always less. That point is always greater. That's an example. So another example is here we have the greatest and these are all the examples from the book. Right? And you take the integral of the function, it's something like 4 plus 0. Integral what is so integral something like and keeps increasing. So here small change in x, right? Say from here to here, great change in or considerable change, you can say. F of x. This is f of x, a of x. Okay. But here small change, also somewhat of a small change, even though here and here, small change, considerable small change. Also, notice that this connected. We call this discontinuous because from here to here is not, while this is connected or continuous. So, and this describes the property that the integration of some value equal to f of x is actually something that is continuous. So, continuity is general property of definite integral, which we'll discuss next. That's chapter 2. OBTR.